Hey everyone, welcome to our webinar. We are going to give people just a couple of minutes, or maybe even less, depending on how quickly you get on, to get started. I'm joined here by Anthony Rosenbaum in our consulting side of the company. Accelerate Solutions is what we call it. And we're going to have a great talk today about GPU profiling for native devices and stuff. So looking forward to that. Please hold on. We'll get started properly in just a minute or so. I can see that a lot of you are joining already. Please, a couple of housekeeping things. We will have time for questions at the end. Put them in the Q&A section. There is two panels you'll see at the bottom of your Zoom. One is a chat where, hey, everyone, please say hello. Tell me where you're from, what time zone you're in. And the other one is a Q&A where that's what we'll be moderating. Anthony and I are actually joined by a number of people in the background who are going to help sort of find those questions that can be answered in the Q&A, and those ones that we'll sort of throw to us on camera. So there's a bit of a team there. And then at the end, we'll also probably bring on a couple of Anthony's teammates to also assist with Q&A, where they all have slightly different sets of experience. So we're working with different customers. So looking forward to that. We're going to give it one more minute. Looks like we've got a few hundred people. I'm just going to here. Wow, I didn't realize we were going to be that global today. South Africa, a whole bunch of stuff in Europe, it's like South America. Yeah, fantastic. Obviously, I'm Australian, but I live in Seattle, so I am a bit of a transplant, and so I feel the people who are in Australia right now if they are joining this call, because it is a little late or a little early, depending on your perspective. Ukraine, awesome. Great. All right, we're going to get started. Good morning, good afternoon, good evening, wherever you are in the world. Thank you for joining us for the latest Accelerate Solutions webinar. Today, we're going to talk about native GPU profiling with my friend, colleague, Anthony Rosenbaum in Accelerate Solutions. He's going to do the majority of the talking. I'm just the figurehead of this talk, where I don't really contribute much at all. But I am, for those of you who are wondering, the product marketing lead for Programmer, for the editor and the engine or runtime. And I've been in the industry for about 30-something years, half of it being a programmer and half of it being in the dark side of marketing. And so I've sort of seen things that probably you have all seen as well. And some of that being things like trying to write the first demos for the Xbox One in C++, being a C# programmer. That was an experience. So I'm really looking forward to this talk. I hope you are too. And I'm going to actually just throw right now straight over to Anthony. Anthony, do you want to introduce yourself and bring up the slides?
Yep. So hi, I'm Anthony Rosenbaum. And today we're going to be talking about native GPU profiling. That is truth from the GPU. I am part of the Accelerate Solutions team. And what we do are things like project reviews, where we'll look at a customer's project, run it through a whole bunch of profilers, get some data, write a report that offers some suggestions on performance improvements and optimizations, and try to make the product even better. So today, we're going to be looking at profilers, GPU profilers. We're going to start with what Unity offers, and then we're going to look at some platform-specific tools. For Android, we're going to look at RenderDoc. For iOS, we're going to look at Xcode. And for PC, we're going to look at NVIDIA Insight. For the profilers, we're going to discuss how to connect them, how to determine the longest draw calls. And we're going to look at the draw calls to see what's going on there, and then we'll discuss some potential solutions. Because we're covering so many profilers in such a short amount of time, it's good to note that profiling takes time. It takes time to start your application. It takes time to connect your profiler. It takes time to connect, and it takes time to replay the capture. Because of that, that could take 1 to 10 minutes, depending on your application. So we're not going to do live profiling. Instead, what I'm going to do is show you screenshots of what to expect when doing captures with all of these platforms. So why are we doing this GPU profile? Well, what you're going to find out is that the Unity profiler doesn't give us the information about what's happening on the GPU. And so there are some times where you've configured things a particular way, and it's causing the execution of the GPU to be slow. And the best way to determine why that is happening is by using a GPU profiler. Now, I have provided this repository. Feel free to download and build to your device of choice. You should see a similar type of profile. It's basically configured to be unperformant right now. So if it's not running very good, then I did my job right. So let's take a look at the scene in our project. I did add some light mapping. I added some isolated real-time lighting, and mostly some stock URP settings and post-processing. For those who don't have the project, I will be going through it, but here's a little overview. It's a very basic tennis scene. And so as you can see here, it's just running an animation at this point. It is not actually playing tennis. So the first thing you might notice if we go into scene view is that we have this big vignette. That is a global volume. And it's a little distracting, so I'm going to just turn that off for right now. But notice that we have bloom in here and we have vignette. We can turn that off. We have multiple cameras because it is a sports game. You need to look at the view from different points of view. And then finally, also, we have some different lighting settings. So here's a baked light. And what it's going to be doing is that it's set to mixed, which is basically going to do some light baking, create some light maps, which I've already done. And it is lighting all this static material. And it's mixed because if the ball or the player got into the shadow, it would actually cast shadow on it. It would sort of turn into a real-time shadow, real-time light at that point. And then we also have this directional light, which, if you notice, is set to not render on the mapped level, on the mapped layers. And so here you can see that this is set to mapped. If I set it to UI, you can see the lighting changes dramatically. So one other thing that we want to be aware of is our quality settings here. For most of the captures, I used the balance. And I did configure all these so they should essentially have the same bad performance regardless. But I want to take note that depending on what quality level you have, you can select different URP assets. You can assign different URP assets. And these URP assets have a whole bunch of configurations for the rendering pipeline. And so we're going to basically use balanced for this. And if I select one, we can see all sorts of options over here. And we also see this thing called URP balance renderer. This is renderer data. And if I click on it, you can see it's another asset. And we have additional information, and we have this screen space ambient occlusion render feature. This is stock stuff. Depending on the version of Unity, it might be included in your sample scene. All right. So now that we see how it's all configured, let's jump into it. So on the Unity side side of things. We're going to look at the profiler. We're going to talk about the markers, what they do, and we sort of break down what's happening on the rendering setup side of things. We'll also just barely touch on the frame debugger and the stats window, as they also give you some helpful information. So if you were to take my project, put it on a device, and play it in its state, you would see something like this. This is a GPU bound frame. And I say that's GPU bound because the GPU is taking too long. And we know that the GPU is taking too long because this GFX present frame here is at 30 some milliseconds. If over here denotes the beginning of the frame, and this line here denotes the end of the frame, we can see that this marker is stretching into the next frame. And if we look over here, we can see that the previous frame's present frame is pushing into the current frame. And where it stops is where the current frame's rendering starts up. And so you are essentially bound by the GPU at this point. And 32 milliseconds is an awful long time. It's added together with everything else. That means it's 62 milliseconds. This is like a 15 FPS game at this point. So if we zoom in and just look at the rendering setup here, we'll see some distinct patterns. Notice how we have like this repeating pattern. And if we didn't have this here, we'd see a fourth pattern here. What I've done is I've selected the render camera stack, and it tells us that there are 4 instances of it. And we know that there's 4 instances of it because there's 4 cameras in the scene. And although I'm only looking at one camera, all are being rendered. And that's a big no-no because each camera requires a lot of processing in order to do culling and shadows and prepare all of the draw calls. So if you're not actually going to look through a camera, you should probably turn it off. And so if we just turn off the cameras and just have one camera rendering and made a new version of the project and captured it on device, we would see something more like this. Our present frame went from 30 milliseconds to 3 milliseconds, a huge win. We are no longer GPU bound. It is no longer pressing into the next frame. In fact, we see this wait for target FPS. This means it's basically waiting for your target frame rate. So here it's set to 30 FPS, so that's why we have this downtime. This is what we want. You want this extra time. This allows you either more time to add gameplay logic early, or if you want more graphic juice, you have the time that you can afford it. So let's just take a quick look at what's happening here. If you are more familiar with built-in render pipeline, this would be all green. Here in URP, which is a scriptable render pipeline, the blue represents the scripts. The green represents what's in C++ or native code. So in built-in, everything's in native code. While the scriptable render pipeline, a lot of that code was moved into C#. And that's why we call it a scriptable render pipeline. In general, a camera has to go through culling. Then there is setting up shadows, rendering opaques and transparents, and then setting up post-processing. Once all of these objects are processed, it's then dispatched to the GPU to actually render it. Now, it's a good thing to note that this is not 100% accurate of how long it's taking on the GPU, but it's a good estimate to start with. So, our Unity frame debugger. This comes with Unity. It indicates how many draw calls are needed to draw this scene. And you can move this line across and it'll select a particular draw call. Here you're seeing an SRP batch is selected. And what's nice is it will tell you why things are not batched with its previous draw call. It also has a lot of information about the shaders being used for that draw call. We also have the Unity game view, which shows the frame rate, your triangles, vertices, batches. This is all in the editor, of course. One thing to note about the batches is that it's representative of the static and dynamic batcher. It is not showing you what the SRP batcher is doing. So, RenderDoc. RenderDoc is what we call a GPU debugger. It is not a profiler because the timings are subject to change. Usually with a GPU profiler, you can replay the frame and it's going to give you the exact same numbers every time. RenderDoc sort of has it move a little bit. And that's because that's not its concern. Its concern is for debugging things on the GPU. We won't go into that, but one of the cool features is that you could change a shader in real time and replay the frame and see if your changes made it more or worse from a performance point of view. Since these numbers are not accurate, we use them more as percentages and ratios. The long ones are still the longest. It's just we can't say that that number of 5 milliseconds or 20 milliseconds is 100% accurate. You can use RenderDoc for Windows, Android. We actually allow you to do captures from the editor, also with RenderDoc. And if you're using Oculus, there is a specific version of RenderDoc for Meta. So the connection process. If you're going to use Android for RenderDoc, it's going to use the ADP protocol. Now, we're not going to go into ADP as that's beyond the scope of this presentation. But if you've ever deployed an app to an Android, you're probably already set up for ADP. When your phone is registered with ADP and recognizes it, when you go into RenderDoc, you should see your phone at the bottom left corner. And you can click on it. What it's going to do is deploy a RenderDoc app to your phone. You'll see the RenderDoc icon across your device. And then once that is dispatched, when you connect, when you go look for an activity by hitting the 3-button menu, you'll be looking on the phone and not on your personal computer. And then once you've found your application, you'll launch it. So what does that mean? Here's RenderDoc. This bottom left corner, if your phone is recognized by ADP, it'll show up down here. And then you'll want to hit this 3-button menu, 3-dot menu over here. And you would see something like this. This would be all of the activities on your phone. If you see something like C drive, then you've lost connection. You probably had to reconnect to do that again. Ultimately, you would find the application you're interested in, and it looks something like this. If you deploy with Android Studio, it might be named default activity as opposed to Unity player activity. But be aware that this name is what gets configured in your project settings. And then with that all loaded, we'd hit launch right here, and it would start up your game. So what you'd want to do is you'd go to your game, you'd play it, you'd go to the point where you're seeing bad frame rates, and you want to take a capture. When you take a capture, it's basically going to do a freeze frame of what's happening right there at that moment, and it saves it. And then we'll replay it on the device. Things to note, though, is that Android's a bit unstable. When you do a capture, sometimes it'll disconnect immediately, so you got to reconnect. Depending on if you're using too much memory already, you might want to, you might not be able to do a capture, so you might want to lower the resolution in your quality settings. Some other reasons why things might not connect is that you might have multiple networks. Maybe your device is on one network and your computer's on another. Be sure they're on the same network. And also, are you using ADP elsewhere? If you're using the Unity Logcat package, that uses ADP. If you're using Android Studio, that uses ADP. If you're already connected to like another device, like an iPhone, and then you try and connect to your Android, it might not work as well. So just try to only have one device connected and make one use of the ADP protocol, that's your best chance of having it connect and make it capture. If it does capture, you'll see something like this. Basically a screenshot of what you just captured. We can see that I'm using Vulkan. If it was OpenGL, we would see GLES. And what I would do at this stage is I would save it, because by default, RenderDoc saves to the device. And if a connection issue happens, you could lose this capture. By saving it immediately, you copy it over to your local drive, and then you can reconnect later and replay it. Pro tip. So when you're ready to play it, you double click it, you'd see this dialog, and you'd see something like this. Here is our timeline, here's our event viewer, and then this area is where we're spending a lot of our time. For RenderDoc, we're going to go deep and we're going to look at different tools. For Xcode and NVIDIA Insight, we're not going to be looking as deeply, but just be aware that all the tools that we talk about here in RenderDoc are represented in other profiling tools. You just have to look around for them. But basically, there's going to be a timeline that shows us our profiling markers. There's going to be a set of draw calls or events, which are the instructions to the GPU. We're going to look at the textures for each draw call with the texture viewer. The mesh viewer shows us the mesh for each draw call. The pipeline state shows us the pipeline, the shaders for each draw call. And the resource inspector shows us all the assets for the capture. In RenderDoc specifically, we're going to be looking at this performance counter viewer, which is going to show us some additional values for the draw call. Most importantly, GPU duration, meaning how long it took to execute that on the device. So what I've done right here is I took that bar and I lowered it, and see this pluses, I just started expanding them. And here we can see the timeline. It looks very similar to what we saw in Unity. One thing to note, though, here at 560 events, this event ID corresponds to this event ID. So here I've selected a particular event. It jumped to the corresponding event in our stack. And because it's event-based, what we are seeing is how many events are going on. One might think bloom is a big problem because there's so many events going on. These are not representative of time at this point. They're just representative of how many events. Next, we're going to look through some of these tabs. And here's the texture viewer. What it's doing is it's showing us the state of the GPU with this selected draw call or event. And the texture viewer shows us what input textures and what output textures are needed for this draw call. I've also done a couple things. Depending on your graphics API, the frame might be upside down when you look at it. And so you can right-side it up with this button. This is basically because DirectX and OpenGL and Metal, they have different coordinate systems. So we have to make adjustments based off of what rendering platform you're using. I've also selected this overlay to be wireframe mesh, which basically says anything that is being rendered this frame or this draw call should be displayed as a wireframe mesh. And so here we see this little capsule of the player being rendered as a wireframe mesh. So if we look at the mesh viewer, we can see the actual capsule. This is the input of it. If you wanted to see it in space in the frame, you could click on VS out. Here are all the vertices. You can go down this list. You can change the vertices in real time. That's why it's a debugger. Here's our resource inspector, basically all the information for this particular capture. We can see a whole bunch of my light maps right here. Our pipeline state, this VS means vertex shader, FS means fragment shader, CS means compute shader. Notice with VS selected, we can see universal render pipeline lit. So this is the shader that is needed for this particular draw call. And I think in newer ones, he's actually spelled out the words. And then finally, performance counters. By default, performance counters will not be a tab. You have to open it up. You'll go to Window, Performance Counter. That will create the performance counter viewer. And we're interested in this button. We'll hit that button. That will open up this dialog. Depending on what graphics API you're using, you're going to see different types of markers. Because we're in Vulkan, we're going to see the Vulkan markers. We're only really concerned in our examples here for GPU duration. Just be aware you have a lot of other metrics that you can use. In OpenGL, though, I think it's only GPU duration. If you're using this on the Oculus for Meta, RenderDoc for Oculus, you will see a section for Meta as well and their own particular markers. So what we'll do is we'll select GPU duration and we'll click sample counters. That's going to make a list of all of the GPU durations for the draw calls, and then we can filter them by their size. And that's what I've done here is I took GPU duration, filter them the most expensive at top, and I made this lovely animation for us. And I want to point out that the top 4 markers all reside within screen space ambient occlusion. Screen space ambient occlusion basically adds a nice soft shadow for objects. And in my game where I'm just using primitives, where there's probably never going to be a soft shadow, I could say it's probably not needed. There's some other costs to screen space ambient occlusion that we'll talk about. But just note that for this capture, we know that screen space ambient occlusion is by far the most expensive feature that we've added. So let's look at the next one. So I went to the 5th one and notice how it jumped over to this shadow area. And so I would say, oh, that's interesting. Let's go look at some of the data. And I look to the texture viewer and we'll see the shadow map. And if you remember, all the real-time shadow is just the ball and the players. And that's a lot of empty space, a lot of unused texture space. And I look at the size here and I go, oh my gosh, it's 4096 by 4096. Just clearing that could take some time, a little less populating it. Maybe we should downscale our shadow map texture. Then we go to our next one, and then lo and behold, we hit bloom. And so, okay, bloom is showing up as one of the more expensive things. Maybe we can reduce iterations on that. Now, we were just talking about screen space ambient occlusion. I wanted to show you something. Screen space ambient occlusion requires the depth pre-pass. And as you can see in this animation, what it does is it basically renders all of the scene into a texture. If you've never seen what a depth pass does, this is what it's doing. You can turn this off in our URP asset, but certain features like screen space ambient occlusion require it to be on. So even if you turn it off, it's going to turn itself on. So it's good to be aware of what features are turning what on. If you've never seen what a depth buffer looks like, here you go. This is the final texture. And what I did is made the histogram teeny tiny, teeny tiny, so you can actually see the data in there. All right, so now let's look at iOS. In order to do iOS, what we have to do is change the project file. We're going to have to change the scheme. We're going to have to force metal on the set GPU frame capture. We'll then launch the application with Xcode. We'll see a new button, M, which will allow us to do captures. It'll do the capture, change Xcode into its GPU state, and then we'll want to hit a profile button to get some actual statistics, and then we'll look over the draw calls. So what does that mean? Here in our project, I go to Product, Scheme, Edit Scheme. That opens up this dialog. When we're in Run, Options, we want GPU frame capture to be set to metal. Then we would press play. It starts up the application. Your console starts going. And lo and behold, this new button will appear. We'd navigate to where we want to do our capture. We'd hit our capture. A few minutes would go by and this cool animation would swipe it up. And what you would have is this. Right now, we do not have performance data. We would want to hit this button. And now we have some performance data on this particular device. The frame is taking 18 milliseconds to render. Now, that's a number that's reliable and we can always use as reference. And now that we have this number, we can expand this area and we can start to see where the time is going. And so what I've done is I've expanded it. You can see here for a single camera, it's taking 100%. We go and break that down even more. If you don't like percentages, we can try, you can also do milliseconds. It might default to nanoseconds by default, but you can adjust those in settings. I prefer percentages. Just be aware that you can change it with the right-click menu. And here, if we look very closely, we can see that main light shadows at 24%, screen space ambient occlusion at 24.8%, all of post-processing at 28.1%, and then bloom at 22.1%. So individually, screen space ambient occlusion is again the most time-consuming one at 24.8%, followed by shadows, and then our bloom. So we're seeing consistent results on different devices. Maybe that's a clue of we want to adjust these features. So let's look a little bit more. If we expand the screen space ambient occlusion, we can see where the time is going. So if you're writing your own shader and your custom render feature or something, and you want to see how it's performing, you can sort of get an understanding of how it's being broken down by using your draw calls in your GPU profiler. If we jump over to the shadow area and we expand the draw call, these attachments, geometry, bound resources, and such, these are essentially the same as those tabs we saw in RenderDoc. So they can show you the additional mesh and stuff like that. But just selecting the top one still gets you a lot of useful information. And the most important thing is here we're seeing this temp buffer 4096. This is the finished shadow map. So we're seeing consistent behavior. And again, a consistent large shadow map being used. All right. So NVIDIA Insight. This is going to give you some really accurate timings. If you're using Vulkan or DX12, there's even more cool features that's beyond the scope of this presentation. It's used for Windows, and it's also used for Nintendo. So if you ever do Switch development, Nintendo provides a custom NVIDIA Insight that works with their product. In order to get NVIDIA Insight to work, you're going to have to configure your NVIDIA control panel, allow for GPU counters. Then you're going to start the application with Insight's frame debugger. When you get to the point that you want to take a capture, you'll hit capture for live analysis. And then whatever you're interested in, you'll hit the right click on the frame and say you want to profile the frame, and that'll open up our range profiler. And we're going to be looking at top sols or speed of light. So here's your NVIDIA control panel. Allow access to all GPU counters. Here is NVIDIA Insight. We go up to connection, hit connect. That opens up this dialog. Navigate, find your application. With frame debugger selected, hit launch frame debugger. And then you would see something like this. At this point, on another window, likely there is the game running. Go to where you want to take your capture. And you'd hit this capture for live analysis. And you would see this loading screen. And then you'd see something like this. And off the top, it looks sort of similar to what we saw with RenderDoc. We have a little timeline. We have a call stack or events. And then we have miscellaneous information. And there's our screenshot. One thing that's nice about NVIDIA Insight is by default, it's set to unit scale. But what we can do is we can change it to GPU duration scale. And we can see what it looks like based off GPU duration. And here we get a very nice visual clue that guess what? Lo and behold, screen space ambient occlusion is the most expensive thing going on in this frame. This backs up everything we've seen on the two previous platforms. The other thing to note, this is running off a Windows build. Here is the time it took to execute it at 3 milliseconds, where on the iPhone it was taking 18. It's no surprise that on my big beefy desktop, it's only taking 3 milliseconds. So if we want to get more information about screen space ambient occlusion, we would want to right click it and we'd hit profile frame. And that would open up this range profiler. And here, what we're interested in are these top sols. These are the top 5 things that the profiler thinks are a concern. Now, there is an article attached that you can read later to get an understanding of what all these things mean. But what I'm going to do is I'm going to hit this little expander, and it's going to give you a nice visual clue. Basically, SM are instructions on the GPU. Texture L2 VRAM, this is texture lookup and various caches. And then CROP is color operations. So what we could say is that SSAO is doing a lot of operations on the GPU. It's probably drawing out to a temporary texture or to the screen. And it's also accessing textures quite a lot. And so if you wanted to adjust a particular feature that you're creating, you would use this data to perhaps have less textures or smaller textures or less instructions. It all depends on your particular scenario. So now we've seen how to see this data on multiple platforms. Let's look real quick on how to fix this. Well, we can disable cameras when not in use. We can remove the effects are not needed. We can disable unnecessary passes like the depth pass, and we can reduce the shadow map. And maybe use cascading style sheets. What does that mean? Well, cameras. If we don't need them, we can turn them off. Turn them on when you need them. If we have to have bloom on, maybe we'll have skip iterations here and we'll reduce that. That can help bloom a bit. I'm going to turn off vignette. Woo! Let's turn that down a bit more. Maybe just turn down the intensity. There we go. Now we can also look at the shadows real quick. So we're using the balanced. And here's our shadow map. Notice it's at 4096. Let's say we want it down as small as possible. Notice the shadow goes down real low. But what we could do is crank up the cascade count, and that sort of helps. Maybe we actually want to do 512. There we go. Now we have a nice, relatively crisp shadow, and it's using considerably less shadow texture information. And then finally, that depth texture, if we wanted to make sure the depth pass is turned off, we can turn that off right there. If we don't like any of these global effects at all, what we can do in the renderer data is we can just turn off post-processing. That's a quick way to do it. Or if we want to make sure screen space ambient occlusion is off, we can turn that off, or better yet, remove it. So let's say we go and do all this. What's the results going to be? Well, one thing I wanted to point out was if you do a capture in the default state, you are going to see all 4 cameras inside a render dock. So here's what it would look like with all the cameras on. It should be a very obvious clue of maybe I need to turn off some cameras. The next thing is this is what the shadow map looks like when cascades are set to 4. Basically, it's breaking up the shadow map so that you can have higher resolution at greater distance. But it does take time. Notice that we have 4 sections as it's rendering different parts of the shadow map. However, if we compare the results of the 4096 to the 256, we can see that they're essentially the same. Yes, there's some artifacting. This is at 256. That's why I went up to 512, because 256 didn't give me the shadow I was really looking for. So if this is where we started at 560 events, if I turn off all of post-processing and get rid of the screen space ambient occlusion and not even do cascading styles or cascading shadows, what we would see is something more like this, where we're at 150 events. You can see it's a lot smaller, a lot more simpler, and it will undoubtedly run a lot faster and consume less power. So again, here is our repository. Feel free to repeat this experiment. I highly recommend that you all learn what features turn on what. It's always great to profile early and often so that when you introduce something, you know that it's not causing a big bottleneck. And then finally, here's a link to the NVIDIA Insight documentation. I'm sure my colleagues will be sharing that in the channel. All right, time for Q&A.
Thank you, Anthony. Thank you so much. As expected, I really enjoyed that. I loved diving into that stuff. I geek out, even though I probably at the point where I write code well enough to be really dangerous, as in I write it poorly. But yeah, we've got a number of questions. I wanted to highlight two things. One, if you haven't asked your question in the Q&A, I won't be able to see it, so please put it in the Q&A. We have too many questions to answer right now. A good thing, but maybe not for you who unfortunately won't have your question answered. I want to highlight that tomorrow we have the Graphics Dev Blitz Day being run by the other graphics team internally. And you are all welcome to join that. I've put the link for that in one of our link slides, which comes after this. So please check that out. That's like a 12-hour period of time where our graphics engineers and product managers are all there answering the questions and really helping you out with individual sort of scenarios. And I noticed there was a couple of questions in here, Anthony, that I'm not going to ask live, but were about specific scenarios that someone might have in their particular project. Just because we've got so many, I'm going to sort of do the more generic ones. Something really, really fundamental: how to avoid stutters in a 60 frames per second game. If you want to do fixed time steps and things like that, should you set the target frame rate to 61? I've heard that many times. What's your opinion on how to avoid stutters like that?
I think it would be important to understand what's causing the stutter. Usually that is a result of some type of spike. Maybe that spike is gameplay related. It might be GPU related. So what we would usually do is we would first jump in with the profiler, try and understand where the spikes are happening. And if it is, for instance, if it is related to the garbage collection firing off, you would want to turn on incremental garbage collection. If it is sort of gameplay related, as I did in my native CPU profiling last year, look at the code, see if there's a way that you can move some of that work to worker threads or time slice it. If it is GPU related, then do what we did here. Do a capture, look for the longest frames, and see if that is what is expected.
Great. I think that makes sense. On that, I'm asking questions out of order. As you said in your talk, Anthony, RenderDoc isn't a profiler. It's more a really powerful and useful frame debugger. What's your strategy for profiling GPU on Android devices? Is it the same as what we outlined today, or?
Yes, there are some other Android profilers like Snapdragon, but they tend to be hardware specific and not as intuitive. So we generally use RenderDoc as the starting point. If it doesn't connect, because sometimes it doesn't, if there's just too much activity going on or they're using too much memory, then we'll try and explore other avenues. But RenderDoc tends to be our main staple of a tool for Android.
Awesome. And then on that kind of like tools thing, does Insight connect to Android and iOS devices for analysis?
It does not, but it will work in Linux and some other platforms, just not on Android.
Okay, cool. I'm going to go back to the very first question that was asked to make sure I cover it, which was someone asked, how can you tell if a specific shader variant is being used or not in a project?
Good question. The best way that I have found if a shader variant is needed is that when you are doing a capture in Unity with the Unity profiler, you will see something that's like create shader. And if you mouse over it, it's going to tell you the name of the shader, the pass, and the keywords. Those are all the things that define the variant. What type of shader, what pass, and what keywords it is. And you'll probably see a few milliseconds later, maybe one with the same pattern, but one's gonna say vertex and fragment. So it's basically compiling both of those. It's not necessarily going to tell you what is being used. It's just saying that this was needed, so I need to compile it and put it into memory.
Right. Yeah. Yeah, I'm just following along, Anthony, to be honest. I'm like, yes, I understand, I think. So hopefully the people in the audience are much more on top of their graphics programming than I am.
You can, of course, look at that. Thinking about that, you can also look at the frame debugger. It will show you this same information. So as you are going through the draw calls, you can just look at all the shader information over there, and it should essentially tell you what type of variant is needed for that particular batch.
Awesome. Thanks. That helps me a lot. Someone asked a question that I'm going to answer, which is, are the questions be answered offline after the meeting? What we normally do is we normally collect all the questions, collate them into sort of common areas, and then determine, like maybe a follow-up blog post or forum post. So rest assured, all the questions will be looked at, and if appropriate, we'll address them in some form for you. Back to you, Anthony. What about I've got a lot of comments that are more comments than questions. The way Unity interacts with shader compilers, it doesn't allow the generation of debug data to be exported into a PDV. How would you approach debugging GPU crashes where the embedded shader debug data can't be used?
Great question. I'm going to preface this by saying that I am not a graphics engineer, but I brought two graphics engineers with us, Cole Ingram and Stephen Cavan are here. And would either of you like to field this one?
Yeah, I can start. Basically, so in my career, shader PDBs have always been really hit and miss. So when you're dealing with graphics crashes, also with graphics crashes, you don't necessarily know if it's all of the vertices or all of the fragments that crashed or just one specific instance. So there's no guarantee that a debugger would even help you figure out what happened necessarily, because it might be debugging a different fragment. So typically my approach is to, one, check for any resources that are corrupted or just missing. So missing textures, missing compute data, or something like that didn't run. And the next thing is just kind of like printf debugging, just start commenting out parts of the shader and see if you can repro the crash, and then use that to whittle down what happens. And then hopefully between that and reading through the code and reasoning about what kinds of things could cause a GPU crash, you can find it. But yeah, it is a very difficult thing to do. So good luck.
Oh, thanks, Cole. Okay. That was kind of helpful. I don't envy anyone who wants to debug in that way, but if that's the way you have to do it. On your actual demo, Anthony, I think I might be able to guess the answer to this, but someone asked, why didn't you just decrease the shadow distance? That helps a lot with quality, and that way you don't need like 4 shadow cascades.
Absolutely. But this was an example of how to do things wrong. So probably not the best way to do it on a final product.
Are there any plans to implement pre-renderer C buffer data overrides that don't rely on the material property block?
I'll have to defer to my experts. Do you know of anything?
I just said we can't comment on any of the engineering roadmap beyond what's on the website. So go check the website there, and if it's not there, we can't really say anything beyond that.
And just to clarify, Cole, when you say website, you mean the product roadmap section of unity.com?
Correct. Which at this very moment happens to be down, but they're working on putting it back up.
Cool. All right. Well, thanks for that, Cole. I'll make sure that I just look at all the plans questions separately. Okay, so is there a difference in performance between base and overlay cameras that people should consider when they're doing this?
Base and overlay camera. In regard to GUI, I'm assuming. And if it's so, the overlay camera requires, or the UI requires a camera in order to render it, where if it's just overlay, it gets injected into whatever the camera is. So one could argue that by requiring the camera, if you have multiple cameras in the scene, it's sort of like forcing you to have an additional camera for your UI, where overlay just will inject it into it. And so you don't need the culling pass and all that additional setup for that extra camera.
Awesome. And the techniques that you talked about today, do they apply to all of our render pipelines built in HDRP, URP?
Absolutely. The markers are going to look slightly different, but you can definitely use all of these tools on all of the pipelines to see where the bottlenecks are.
Awesome. I've got a longer question here that I'm just going to read out. Even 7 milliseconds for a C# SRP processing takes a lot. Doubly so if we can consider that that actually happens on the main thread. Why don't we get any access for command buffer API when working off the main thread? And why is culling a synchronous operation? Because those things could help if they weren't that way.
Great question. I'm going to refer to my experts.
Howdy. So the reason you don't have access to the command buffer API is because it's part of Unity's managed C#, and only the managed code can go along and run on the main thread because you're dealing with a Unity object. It's just a limitation of how C# is implemented for Unity. As for wire culling a synchronous operation, it's not, I mean, the kicking off the jobs do actually start happening on the main thread, but the culling is spread across the cores on the device. Hopefully that answers your question.
Thank you.
Hopefully, yeah.
Yeah, a bit more context too. So the marker that Unity calls GPU or calls culling actually does a lot more work behind the scene, setting up renderers and stuff. So it's a little bit misleading. When you see a giant culling time, that doesn't necessarily mean that frustum culling took a long time. It's that all of the renderer setup that Unity has to do in the back end to move stuff to the render thread took a long time.
And I would like to just side note that one of the costs of culling is that it has to get all the renderers in the scene first before it does any kind of frustum culling. So if you have objects that are pooled and off frame or just not being used, turn off their renderers if you have a chance, because that's going to make that list that's needed, that's being gone through in that culling setup shorter. So the less renderers in the scene at that moment, the faster culling can be.
Awesome. We're only got a few minutes left, so I'm going to ask Anthony if you could go to the next slide. While you do that, I want to actually, could you exit out and refresh this page and then re-show it? If that's
Me?
okay. Yeah.
Okay, hold on. Let me.
And then Cole, Stephen, while Anthony's doing that, do you want to answer a question that's just like, are there any specific considerations we should think about from a VR perspective for this sort of graphics profiling?
I can go ahead and start. I'd say the main one is with VR games, you should be GPU profiling early and fast constantly because you have to render the game twice, and there are also generally less powerful GPUs. Also, I believe most VR headsets use mobile GPU style, or I'm blanking on the actual word, but basically it's more like working on a mobile game than it is working on a PC game. So anything that helps, any strategy you have for mobile games specifically applied to VR, and then just keep in mind you have to render the scene twice, and certain effects don't work because you can see from both eyes, and so certain things that you can get away with on a 2D screen you can't. So basically, if you're working on a VR game, I'd recommend GPU profiling early and often, constantly, because it is going to be a challenge.
Right. Awesome. Thank you. All right. So listen, sorry, Stephen. Yeah.
I was just going to say, if they're developing on an Oculus device, you probably want to use the Oculus version of the render doc. That can give you some good information of how busy the tiles are. Another thing to go along and consider is the amount of draw calls. So especially on a mobile VR device, the amount of time you've got to actually render. The GPUs might be able to go along and cope with all the things you're pushing onto it, but the amount of time it's taking up on the CPU, because they tend to have very few cores, and they tend to be low power devices. So the number of draw calls that tend to be a significant problem.
Okay.
I have one other tip. Avoid transparencies. When you need like leaves and things, put it into opaque paths with clipping. That'll keep it out of the transparent paths and you'll be more performant.
Awesome. Thank you all three of you for answering those questions. Hopefully that was a help to all of you in the audience. I'm just highlighting these three webinars and events. The next sort of webinar we've got in the series, all about how to use Unity source code for those of you who have access. That's coming up on June 8. The partner one I would call from today's native GPU profiling is the CPU profiling, which is already available on demand. So go check that out. Thank you, Anthony and team, for that one. And then tomorrow, as I mentioned earlier, there's a graphics dev blitz day where we have engineers, product managers, and others all on deck answering your questions on the forums, on Discord, and on Reddit. Please check that out if you have specific questions. And it is designed specifically for, if you're having a particular problem in your project, this is the time to be able to ask those questions. Next slide is all about Unity 22 LTS, which is coming soon. We've actually just published the blog post from Ralph Howitt, who's the head of engineering here at Unity. That's all on, that was on our blog. That's the left-hand link. And the right-hand link, we are going to have a live stream to sort of talk through a bit more detail about what's in the LTS. That's coming up really soon. And so you can sign up for getting notified about that. And then I think I'm on the last slide. Yeah. So just a reminder, this is all thanks to the Accelerate Solutions team being able to be embedded in and partner with customers and talk through their challenges and their projects, their dreams and aspirations. And so I really want to thank Anthony and the teams that do that and then able to sort of distill that information and be able to bring it to you in this way. You can see the kind of areas that Accelerate Solutions can help you with. And I highly recommend that if you are having challenges, that team is a fantastic team with a lot of really good insight and direct connections with the engineering teams to get even more sort of action happening there. So thank you, everyone. I hope you enjoyed it. I hope you got something out of it. Thank you, Anthony. Thank you, Stephen. Thank you, Cole. And we'll see you next time. Cheers.